In this video, we're going to define power and look at mathematically what it means and apply it to some simple problems. So first of all, power is nothing but the rate of doing work. So if you can do the same amount of work in a shorter interval of time, you're more powerful. And on the other hand, if you do the same amount of work in a longer interval of time, you're less powerful. So the definition tells us something very simple. The average power is nothing but the work done divided by the time interval. So work done by a force divided by the time interval. Now if you look at the units of power, it is nothing but joules per second, because work is measured in joules, time is measured in seconds. However, it is an important unit, and so it has its own special unit, which is watts. Okay, so it's W-A-T-T-S, watts. You've come across watts with light bulbs and other things. So it's the same thing, it's power. Okay, power delivered to the bulb. Here we're just looking at the power delivered by any particular force. Now we can also write power in a slightly different manner, where we can use the definition of work. Okay, and if we see that if W, the work done, is simply equal to force times the displacement, then the average power can also be written as F times delta X over delta T. And you may all recognize from this equation that delta X over delta T is nothing but the average velocity. So this is equal to force times V average. Now in mathematical notation, average of a quantity is written as P with a dash on top of it, so it is equal to F times V times with an average quantity of the velocity. So we can find the average speed for a motion. If you know the force acting on it, then we can figure out the power from there. Now on the other hand, we can also define instantaneous power. Okay, power delivered at any instant. Instantaneous power as P. Now if you see, I'm just writing P without the average sign on it, and this is simply equal to F times V, which is the instantaneous speed. So this is the instantaneous power. Here V happens to be the speed at any instant, so instantaneous speed. Okay, so this gives us what power is. Let's try to apply this concept to a couple simple situations, and everything should make sense. So let's say that you have an elevator. Let's say that the mass of the elevator with everything included is 1,000 kilograms, and you have a force that is pulling the elevator, some tension, the cable that is lifting the elevator up. And while it's doing this, let us say that it is accelerating the vehicle at a rate of 0.2 meters per second square. And while it's doing this, let's try to figure out the average work done, or rather the power delivered, the average power delivered in, say, moving this elevator for a time of, say, 50 equals, say, 2 seconds, and assuming that it starts at rest. So we'll say that the elevator starts at rest, it's going to be hoisted up, and we're going to figure out the average power delivered by this cable while all this is happening. Okay, so we can use our definitions of of power, average power, as work over time. We can use that to figure out what this is. We can also do this by finding the force and multiplying it by the average speed. So we have several ways of doing this. Let's just use the work concept and see how we can use that. So in order to figure this out, what we need to figure out first the tension in the cable. Okay, now since it's accelerating up, we know how to do this. We've done this a lot when we were dealing with forces. So let us begin by drawing a free body diagram. So I have 9800 newtons pulling it down, I have T pulling it up, and the result is 1000 times 0.2. So this gives me my equation for the force. So it is equal to T minus 9800 is equal to 1000 times 0.2, which happens to be 200. So this gives me T equal to 10,000 newtons. Great. We have one part. We know the tension. Now, either I can find the distance and find the work, or I can find the average speed and then multiply it by the tension and get the answer. You'll see we'll get the both. In both cases, we'll get the same thing. Let's find the distance traveled first. Alright, so let's find the distance traveled first. Now, I'm going to do it both ways. I'm going to find the distance traveled and then obtain the result. I'm also going to find the velocity, average velocity, and obtain the result. And we'll see that they both should match. But this will give us a method of doing both of them. So let's first find the distance traveled. Since the acceleration is constant, we know and we also know the amount of time. We can use this equation: delta x equals vi delta t plus 1/2 a delta t squared to figure out the distance. And this is simply given by VIT, which is 0 times 2 plus 1/2 times 0.2 times 2 square. And this happens to be nothing but 0.4 meters. So 0.4 meters. And so this implies now that the average power is the work over the time. The work done is nothing but the force multiplied by 0.4 divided by the time. Time is 2 seconds. So this gives me my power, and this happens to be 4,000 divided by 2, which is 2,000 watts. So this is the answer. Let us just make sure that the other way also gives us the same relation. Let us find the final velocity first. And we'll use Vf equals Vi plus A delta t, and Vi is 0, A is 0.2, and the time is 2 seconds. So this gives me 0.4 meters per second. Now my average velocity, which is only when an object moves with a constant acceleration, we know that the average is Vi plus Vf over 2, which happens to be 0 plus 0.4 over 2, which is 0.2 meters per second. So now I have my power delivered to be, my average power to be equal to the force multiplied by the average velocity, which is 10,000 multiplied by 0.2, which is equal to 2,000 watts. So both methods end up giving us the same thing. So you can use pretty much anything you want. Just make sure that you're consistent with the definition and stick with it. Now, in this case, we can ask another question, which is namely, what is the instantaneous power at t equal to 1 second? So how much power should the motor that is pulling the cable have to deliver at exactly at that 1 second mark? Now again, our method is very simple. In order to find the instantaneous power, all we need is the tension, which we already have, which is the force, and we multiply it by the velocity, the instantaneous velocity at 1 second. So let us find the instantaneous velocity at 1 second. At 1 second, so this will be simply equal to, we can use this equation, Vf equals Vi plus A delta t. It is 0 plus 0.2 multiplied by 1, which happens to be 0.2 meters per second. And so my instantaneous power at 1 second is simply equal to 10,000 multiplied by 0.2, which also happens to be 2,000 watts. So so that's easy. But let's just do it also at t equal to 1.5 seconds. So you'll see that the number actually changes. So if you look at the velocity at 1.5 seconds is going to be 0 plus 0.2 times 1.5, which happens to be 0.3 meters per second. And now the instantaneous power at 3 seconds, or rather 1.5 seconds, is equal to 10,000 multiplied by 0.3, which is equal to 3,000 watts. So the instantaneous power changes when there is an acceleration. The average can be found by two means, and to find the instantaneous, just find the instantaneous velocity multiplied by the force, and then everything is good. Alright.